Good afternoon. I'm Laure Lebars. I work for WAICF as a research project director, and I'm also the president of QUIC, Quantum Industry Consortium, so an association that we talk about. So today, probably different topics. I don't know if it will be relaxing or completely changing your mind. The idea is really to give you an overview of what exists in Europe in this industry on the quantum computing. What does it mean? What is quantum computing first? And of course, we'll see some use cases with Davide Coppeletto. And we will explain you, so we are in an AI conference, so we will explain you how AI could eventually benefit from a future quantum computer. The other way around is how the AI could help the future quantum computing. How could we prepare it? As mentioned earlier, I will briefly introduce about this, what is this European Quantum Industry Consortium, what do we do, and finally try to give you a brief overview of what exists, or we won't go into detail in any of those topics. The idea is really to give you some hints of what it is, and of course you will have plenty of time after that to look in details. So what it is, quantum technologies, so you probably heard it a lot. So when we talk about quantum technologies, this is something that exists for more than 100 years. You know, Einstein, etc. And today you already use quantum technologies. You have a GPS, we have a DVD reader, etc. This is quantum technologies. You probably heard of what they call a quantum 2.0, quantum second revolution. It's actually a progress. So completely different, it's a progress. But the idea is that we master more and more individual quantum particles. So we can do things that are more refined. And we can do things in quantum sensing, metrology, imaging, so it's one area. Quantum communication, simulation, and quantum computers. So I will not go through all of this because we don't have the time, but that's if you find in the literature or in the internet some, that's those areas they're talking about. So today we will concentrate on quantum computers, maybe talk a little on communication, maybe on sensing as well, but that's the idea. So what is it? And here, my background, I'm a software developer, software engineer, scientist, mathematician as a background. I've been interested from day one on those topics, but I'm not a quantum physicist. So I will explain you with my words. And really what I want you to give you a sense of, you don't need to understand all the quantum mechanics on the bottom to really understand what is the power, and eventually in the future, be one of these quantum software developer or any other jobs that may be created. So remember, probably in the high school or so, you had those basics of quantum mechanics. So you have to remember some principle. First, this wave-particle duality. So those objects, so subatomic objects, we talk about photon, electron, ion, they behave sometimes as particles, sometimes as waves. So that's something we always have to remember. As a consequence of this, it's indeterminism. And here it's a way, if we know one property, we cannot know the others. Example, we know the speed, we cannot know the weight. Or if you talk about an electron, you have the spin. So if you know the spin, you don't know the position, etc. So this is difficult to have. You cannot know everything, all properties, all the values of those properties at the same time. So it's difficult, it's counterintuitive, but that's more or less the basis of what we do later on. And that means also that when we measure, measuring is kind of, we fix this particle to look at the value. But if you think of your electron that is spinning around, so you basically like a mosquito, you slam on it, so you have a value, but it lost this quantum behavior. It is not in quantum state anymore. So measurement, when we measure, we destroy. So when we do a quantum computing, that will be, we will have to find another way around to copy, etc. But that's also what is called a no-cloning principle, okay? And two interesting things that are actually the two properties that are directly used in this concept of quantum bits is superposition. So it means, so here I have to refer to the classical computing. You do 0 or 1, and it's one state or the other. And everything we do for the last 70, 80 years is this. We have a state, we combine state, and we go to another state. And this state is 0 or 1. 0, physically, it's okay, electricity goes through. 1 goes through, 0, it doesn't go through. And it could not, it's one or the other, it could not be both at the same time. If you think, I may go on the next slide here, think of your electron, you have all those possibilities here on all those areas. And we represent the 0 up, North Pole, and 1 on the South Pole. And then you can have all value in between. And if you use this Bloch sphere, it's, you can think of this cosinus and sinus. The sum of the square is equal to 1. That's all what you have to remember. But you could have all value in between. And you can superpose those states. And that's interesting because that means, so let's take two states. So you can have 0 and 1 at the same time with a certain probabilities, etc. So now we can have different ways of representing it. You have this 0 and the arrow, or you can have a matrix representation, and then those alpha and beta. So that's for 1 qubit. So this qubit is using those properties. Now if you have 2 qubits, that's one way, and you superpose the two states. We represent it this way, or we could use the matrix with 2 dimensions, etc. So that's, I will say this is okay that you don't understand how physically it's done. You have to trust whoever is building the quantum, the hardware who is doing it. We represent it. We have a mathematical representation, probabilities, matrix, etc. And we will use those to do the calculation. But remember this, we can superpose 2 state, 3 state, etc. And that means, in terms of possibilities, if you have n state, you have 2 exponent state, which is much more powerful than 0 or 1. And it's one or the other, and you cannot have both at the same time. Okay, it's just one way of representing it. Yeah, and I forgot to talk about entanglement, or intrication en français. Entanglement means if you have, let me go back because I don't want to go too quick on this. Entanglement, it's you have 2 particles, so 2 electron or photon, etc., each on a quantum state, and you entangle them. And that means that they are completely integrated. If you do something, an operation, a measurement, whatever, on one, it has an immediate effect on the other one, no matter how far away they are. If you do something on one, it has immediate effect on the second one, 100 kilometers. It's not speed of light. They don't communicate speed of light. It's automatic. Counterintuitive again, but it exists. We know it. It's the quantum physician, the theory exists for a long time, and now we master it. We know how to do this. We know how to entangle those 2, put it in a specific state with this value, and then put it in distance. That will be very useful also for communication. So if I go back, so a quantum bit is a quantum particle that we master. We put it in a specific state. We know the value, and then we'll act on it. So same way in classical world, you have an algorithm as a sequence of gates, a sequence of transition from one state to the other. And you have operators, and, or, not, etc. A quantum algorithm is exactly the same thing. You have qubit, and you have gates, and you change the state. But in this time, instead of changing from 0 to 1 or vice versa, or not changing, you change all the superposed state at the same time. Okay? And that's very powerful. Then there are specific gates that are specific to quantum computing to do this superposition, those entanglement. But remember that a quantum algorithm, it's the same set. It's a set of quantum state and gates, but again, instead of binary, 0 or 1, you have this multiple. On the right side, this is one way of representing it. That's the way IBM represents it. So each line is a qubit. So if you have an operation, integral, it happens on the same. And of course, the end of your algorithm is to measure. Okay, because we do this calculation at some point. We want the result. I can talk for this on 1 hour, but we don't have the time. So. What do we do now with this? And the theory exists. I mean, people are working on this for quite a long time. Now, in the 90s, we didn't have any quantum computer. Today, we have research computers, but we are close to it, and we have more and more power. But basically, they said, OK, if I have quantum qubits, sure, wrote an algorithm how to factorize the integer. And remember, this is what we use in those RSA key, which is, by essence, an exponential problem if we go on the classical way. So he found a way to instead of having the growing exponentially, it's on a reasonable time. So it's not instantaneous, obviously, but still it's feasible. Another algorithm is Groover, and I will not go in detail, just to tell you it exists. And that's database search. If you have a structured database, an address book, which is really in alphabetical order, you look for, I don't know, Mammy, you go in the middle, it's L, okay, I go in the second half, etc. So you have a limited time if it's structured. If it's unstructured, you can look as many times as there are data. So that could be really exponential. So here, same way, there is a speed up in this algorithm that could work on qubits. Another way to explain it, and it's a caricature, it's not exactly the way it's happening, it's like parallelism. It's like looking at all possibilities at the same time. Again, don't take my words word by word, it's just another approach, another way of processing, etc. And then quantum machine learning. We have, it's more recent, but we do have algorithms. So we have those algorithms, there are plenty. There are plenty of use cases. At some point, we come to the same mathematical problem, so we can use those 3 plus certain, and Davide will give you some example. And of course, that's all the theory. We don't have the machine, they're noisy, they're not stable, because a quantum state could be very easily troubled, so of course it's not easy. But as a software developer, we have to trust whoever is building this machine that one day they will figure out. Now we have to understand how they do it. There could be different techniques. In terms of qubits, do they use electron, ions, superconducting? Okay, we will see. Maybe a combination of those, we will see. But that's coming. That exists. Every year there are progress. So here it's a list. You could look at it later on. And now I will switch to Davide for an example.
Thank you, Laura. Hi, everybody. My name is Davide Corbelletto, and I lead the Quantum Competence Center of Intesa San Paolo, which is a group of people that is committed to research and develop quantum computing and spread, let me say, this technology throughout the bank. Just a few words about Intesa Sanpaolo. It is the leading Italian bank and the third European bank for market capitalization. Besides the data you can see on that slide, I want just to point out the fact that the bank is an ethical one, so is promoting financial inclusion and, of course, pursuing digital innovation. That's why we have a quantum competence center within the bank. If some of you yesterday has had the chance to listen the other quantum panel that was about the research perspective, probably you already know that quantum computing will be a game changer in lots of fields, especially, for example, in pharma and chemistry, because the killer applications are protein folding, drug design, and also designing new materials. But there are lots of use cases also in the financial services, and that's why we started to, let me say, deal with quantum computing in our bank. Also because it is, we weight also according to McKinsey and Boston Consulting Group, total revenue, direct and indirect, about $450 billion in 10 years, starting from now. But which use cases we are talking about? Well, let's start with optimization problem. Optimization problems are really suitable to be solved with a quantum computer because basically you can smartly translate them in a minimization energy problem of a quantum system, and a quantum computer is in fact a quantum system. Then another thing that is really relevant is stochastic simulation, and here quantum computing can be a real game changer because being a quantum device, it is able to generate real random numbers. And so, for example, your simulation techniques like Monte Carlo simulation have a chance to converge, not, let me say, not by chance, but physically. And another thing that is really important is cybersecurity, because of course we know that quantum computing may pose a threat with the Shor algorithm Laura named before to the asymmetric encryption protocols. And so we have a problem because we use this kind of, let me say, of cryptography to ensure the safeness of the transaction, the financial transaction. But it is also, there is also, let me say, a good news, the fact that quantum computing quantum technologies may help also to ensure the communication channel, again with a physical proof. But here we are at, let me say, Artificial Intelligence Festival, so probably the most relevant for you application of quantum computing are the one in machine learning, artificial intelligence. And I will give you an example. This is just a master plan with the relevant milestones Intesa Sanpaolo Quantum Competence Center achieved in the last 4 years. We started our journey in July 2020. But I want to put the focus on the last one, that was our last peer review paper published by IEEE Explore, that is our first research on quantum machine learning. And specifically on principal component analysis, I assume that you are artificial intelligence experts, so you are familiar with these unsupervised machine learning techniques. I just give you an example on of the usage of this technique, even classically in financial services. Imagine you have a matrix of correlation of, for example, interest rate or market rates, and you need to prune it in order, first of all, to clean all the spurious correlation between this interest rate, and then to put the focus only on the strongest correlation. Well, this is exactly what the principal component analysis does. And the point is that if your matrix is really big, you have a problem because the classical technique is not able to give you the answer in a feasible time. And so that's why we started to, in 2022, we started to think about a possible alternative to this, to the classical solution. And with the quantum solution, I don't want now to bother you with the detail. I leave the link to the published paper, so you can read it if you want to delve into a little bit. We basically demonstrate the fact that the quantum equivalent technique has an exponential advantage in terms of time complexity. And it means that you can now cope with, now not, because we don't have the machine that, let me say, can run this algorithm, but in the future, when we will have a coherent and scalable quantum computer, if you have a data set that is from 1 to 2 order of magnitude bigger than the one we are now able to cope with the classical algorithm, you should address the problem efficiently. And so just to properly wrap up this brief speech I gave, I will just, let me say that my intention was to convince you that it's important to start dealing with quantum computing in general, but in particular in financial services, because there is a lot of possible use case to address. Of course, there is also the cybersecurity topic that is particularly hot, and you cannot ignore it. And if I may, it's better to do it not now, not just now, but also in a well-organized and structured way, as we're trying to do in Intesa Sanpaolo, creating this competence center to, let me say, centralize the knowledge and help our colleagues that will need to, let me say, introduce this technology in their workload in the, let me say, near-term future. Thank you very much.
Thank you, Davide. So now Shaim will show us the other way around. So let you explain, present yourself.
Do you have a laser pointer? Doesn't look like it.
No.
Oh, actually, I do. Okay, cool. All right. So QML stands for quantum machine learning, which is machine learning using quantum computers, but I'm not going to talk about that. And the reason is that we don't really have quantum computers yet. What we have are engineering prototypes for quantum computers. And if we work hard at it, maybe in 5 years, maybe in 10 years, we'll have quantum computers that are big enough and useful enough to do machine learning. But we can use classical machine learning, meaning using regular computers and standard machine learning to help quantum reach that point. And this is what I'm going to talk about. My name is Shaim Machnes. I'm CEO and co-founder of Cruise, and I'll tell you a little bit about what we do later on. So this is one example from a paper. Physicists use machine learning a lot now, right? It's become a common tool in physics labs, and this is one example. And what you can see here, this is essentially a standard reinforcement learning agent scenario. So you have a thing here. It happens to be a physics experiment doing Bose-Einstein condensates and things like that, but we don't really care about that. What we care about is that we want the system to behave in a certain way. So we have a camera that takes pictures and tells us whether the system is behaving the way we want it to or not. We have an agent here in the standard reinforcement learning meaning of the word. And we have some weird electronics, etc., that allow us to manipulate the system and observe some of its properties, right? We don't have full visibility. It's a quantum system. It can be in superposition. If you observe absolutely everything, you collapse the superposition. But I can still treat this as a normal RL problem. So physicists do that, and they do that a lot, okay? Not necessarily RL, classification, everything else. Another problem that we're looking at is compilation. So this is a quantum circuit. Each line here is essentially the lifeline of the qubit. And what you see here, the squares, etc., are gates. So if you go back to your kind of classical electronics when we had NOT gates and AND gates and XOR gates and things like that, this is exactly the same idea. And what you have here, these guys, these are 2-qubit gates. And they entangle and disentangle 2 qubits. And the things here are measurements. You measure the qubits, okay? And H and Z are kind of single qubit gates. Now, the problem is that not all qubits are connected to all other qubits. This is an example. This is a layout of a 50-something qubit chip from IBM. And you can see each little circle is a qubit. And if this qubit wants to be entangled with this qubit, you need to go through a lot of qubits to do that, right? The reason IBM is doing this is that if you connect 2 qubits, they can not only entangle with each other when you want it, they can entangle with each other when you don't want it. So by reducing the connectivity, they reduce the noise, quote unquote, which is unwanted effects. However, now making sure that you map your circuit to the right layout, so you don't need to just move the quantum state along the chain from one point to another so you can entangle the 2 qubits, this becomes a problem that you can use machine learning for. And if you're familiar with the problem of route and place for electronics, so when you have you try to lay out a circuit board and you don't want too many wires crossing, this is a similar sort of problem. And people have been using machine learning for that. And this is an example of such a paper that does that. Okay? So that's another quantum problem that are dealt with classical machine learning. Another one is quantum error correction. So we can't really talk about quantum error correction properly because that requires like 4 hours. But I can give maybe a general flavor of the thing. So how does classical error correction works, right? So let's say I take each bit and I multiply it 3 times, okay? So 0 goes into 0, 0, 0, and then 1 goes to 1, 1, 1. And whenever I have an error, I just change 1 qubit. So maybe I go from 1, 1, 1 to 1, 0, 1. So to get from one code word, which is 0, 0, 0, to another, I need to go at least 1, 2, 3. I need to make 3 errors to turn one code word into another, okay? And then if I have only 1 error, I can do a majority vote and see where I probably came from. And this is how error correction works. You take a series of code words, here 0 and 1, and you spread it out in a space that has more code words. Right here, the corners of this cube. And the question is, how do you do this for quantum? And unfortunately, there is no very easy way of explaining it. But the point is that you replace every qubit with a number of physical qubits, but those collection of physical qubits encode 1 logical qubit. So just like in the classical case, we took 3 bits to encode 1 logical bit, and we made sure they're far enough away in terms of how many errors you need to go from one to the other. You can do the same for quantum, okay? But then if I want, let's say, 100 logical qubits, I may need 10,000 physical qubits. Which means that if we're talking logical qubits, we need many, many more qubits. But we also have very, very complicated error correction algorithms. And here people use quantum. But can we use quantum for directly addressing the problem of building better quantum computers? And the answer is yes. Okay? Think of a physics lab. Okay? I plan a device, I simulate all the physics in the device before I build it. I then very carefully build it. It doesn't work. Right? This happens a lot. If you think of nuclear fusion, this is the only thing that ever happened. Right? We plan the nuclear fusion reactors, we simulate them, we build them, they don't work. Why? Because the physics is really complicated and it's really sensitive to initial conditions. And there's a lot of problems there. It's cutting edge science, cutting edge physics. So what you do usually is you put an army of junior physicists to reverse engineer the device that you actually built, to figure out why isn't it working. You know what you wanted to build. The question is, what did you actually build? And where's the difference, right? So usually the solution is, let's put an army of people on it. But in the same way, you can think of Microsoft Copilot as a junior programmer, or you can think of DALI as a junior graphic designer. We can create software that's a junior physicist. And then I can put in the lab 100 junior physicists to help you figure all this out. Right? So how much faster would you make progress if every lab has 100 virtual physicists? Right? They're still junior, but they're doing a lot of work. And this is what the company that I helped found does. We create a virtual physicist. And how does this work? So this is the kind of general idea. You have your quantum device here, and a very, very, very detailed simulation here. And I'm talking kind of excruciatingly detailed, including, for example, all the noises that come on the control lines, because the control electronics is imperfect. And this affects the performance of the device. And then you put a series of algorithms that interact with the simulation and the device and fit the model to the data to try and understand what's going on. Because when a physicist say they understand what's going on, what they mean is, I know how to write the equation that describes the system. This is what a physicist means by understanding. So we help the physicist get to the point where the simulation replicates the actual device. And then they can look into the simulation and figure out which of the 57 noise sources is the one that's limiting. Because in simulation, I can turn noises off individually and see how much it changes the device. Okay? So we can do that. And then you can do a lot of interesting things with it that I won't go into. But one thing I want to mention, that this is actually working. So this is like a graph of the experiments that our software is running every night, and you can kind of delve into the details of it. And I want to give you an example. And I'll be able to, I believe I can tell it in a way that you'll be able to understand what it does. So this is a data set of behavior of a quantum system that we got from a prospective customer. So what you see here is you're trying to move the quantum system, let's say from 0 to 1, from one of two quantum states, okay? And if it's blue, it's in 0, and if it's yellow, it's in 1. Now, there are two parameters here. One is how long are you driving the system, and the other is kind of how hard at which voltage, okay? And they gave this to us because this didn't work really well, because it's supposed to look like this, and it actually looks like this. So what our software did was essentially run a whole bunch of simulations and optimize the model until it learned to replicate what was found in the experiment. Okay? And this is the simulation after learning. So this is essentially machine learning to optimize a simulation to fit a data set. Okay? And as you can see, these two look very much alike. We were successful. But because the model is very rich, you can always say, yeah, just overfitting. So how do you know? So you take the learned model and you apply it to a different experiment of the same system. And the experiment looks like this. Again, it's supposed to look like this, but it looks like this. And if you use the learned model, the simulation returns this. So actually, maybe it did really learn what's going on. But then you can do something else. You can use the information that we learned to know how to fix and change the way we're driving the quantum device. And when you do that, we get that, which is very close to the ideal. Now you'll notice it's not perfectly ideal because, for example, there's more yellow at the bottom here, and it's not symmetric as it's supposed to be, but it's pretty good. So this idea of using machine learning to help build quantum computers, help make them better, it actually works. And this is the physics thing. Now, one day we'll have great quantum computers and we'll be able to use them to do amazing things with quantum machine learning. But until we do, we can use machine learning that works today to help reach that point. And this is what we do. And by the way, we're raising seed funding right now. So if you happen to be a VC, talk to me after this. And thank you.
Thank you, Shai. So you see, we have plenty of examples. We can go on for hours. So it was just to give you an idea of what exists, but of course, you can go deeper. I was asked also, and I'm representing here QUIC, so European Quantum Industry Consortium. It's not a consortium, it's an association, but that makes a nice acronym, so that's the way it's called. So this is an association of mainly industry, but also research, academy, RTOs. And the idea, I mean, let's call it a spin-off of the quantum technology flagship. But the idea was that, okay, there are really good research in Europe. There is a lot of companies that exist already. We have skills, we have the workforce, but we need maybe more to collaborate all together, have this sense of ecosystem, build networks, etc. So that was based on this, on those. So as I said before, it's a non-for-profit association founded almost 3 years ago. So we brainstormed the first lockdown, started the second lockdown so if we can maybe go here to just, you have some logos, not all, but give you a sense of the diversity of enterprise. And it's all quantum technologies, by the way, I forgot to specify it. So it's not just quantum computing. Here we go back to those sensors, metrology, imaging, communication, simulation, and computing. So all technologies, and of course, the enabling technologies, example, photonics. And all size and all, so European in a large sense, so not only EU, but also associated country or candidates. And just to give you an idea, so that's October, it's more or less the same figures, but you have close to 60% are SMEs, so startups and SMEs are part of members. So what do we do? So we, as I said, we have all technologies, so we have expert group on those different aspects, on those different pillars. But we also have those working group on education and skills, standards, IP and trade, ecosystem, etc. The idea, take the example of standard, is we don't define standard. We are not a standardization bodies, but we see it all together and exchange and define what are the needs of us as industry, and we interact with those standardization bodies, so SENS, NLEC, ISO, etc., whoever, and depending on the technology, could be a different group, by the way, etc. So that's what we have behind. So here it's another way of viewing it. So that's the name of the working group. You can find it on our website, and on the other side, you have those expert group, and including enabling technology, as I said, not just the pillars. We also have national chapters. So in each country where there are members, we have national chapters. The idea here is to help those SMEs and startups to find what exists locally. So not just those European Horizon Europe or Digital Europe funding, but also national, private as well. And that's also the working group SME and funding. By the way, some VCs are also members of QUIC. So that's we have direct access to them. There are equivalent in US, Canada, and Japan. So QEDC, QStar, and KIC. And we form, so equivalent in the sense that also industry, quantum technologies, etc. We have this International Council of Quantum Industry Association, but we may work more directly in the future. We also, of course, interact with national, Le Lab Quantique, QTAC in Germany, Lab Quantique in France, etc. And we interact, it's not shown here, but we have a privileged dialogue with the European Commission. They are, of course, interested in what we find out, what we produce, like the strategic industry roadmap, a part is public, a part is for members only. That includes also critical components, etc. We had a working group also, a task force on the G7, probably have one this year as well. So just to give you an overview, I mentioned the Commission. We are also, as the association is a consortium partner of the Coordinated Support Action for the European flagship. And basically, we are the only one, even if not technically an industry, we are the only one representing the industry, more or less. We are also active in some other EU initiatives. So I name a few here. EuroHPC. So EuroHPC is a joint undertaking between different member states, and not just EU member states, but also other states like Norway, Iceland, and the European Commission. And so there are two aspects: the infrastructure. So there is they build infrastructure, and research and innovation project on those as part of EuroHPC. And since 2000, the second regulation on EuroHPC, quantum computers are included. That means quantum computers will be acquired by the GU, installed on those different infrastructure or already done. That will be great to test those hybrid architecture, and also, of course, giving access to SMEs, etc. And there are plenty of things to come. And remember, EuroHPC is also the one, you probably seen it last week or before last week, the AI, how they call it, AI package, they call it, innovation package. So here they will make sure that those HPC, eventually including quantum computers, are dedicated to AI. So I mention it here because it's an AI conference. How QUIC interacts? QUIC is a private member next to ATP for HPC and BDVA associations. So we are sitting on the governing board. No voting right, but still we can voice our concern. We are sitting on the Research Innovation Advisory Group, etc. We also, I'll not go in details, but CHIPS Act is also currently cooking. So the new version, there will be a GU, there is a GU. There will be plenty of things to do. And of course, there are some quantum chips as part of it, etc. Okay, EIC, EIB, I will not go into all those details, but just to tell you that that's the kind of thing we are doing. So as QUIC, and of course that's a way to help our members and to bring our forces together and collaborate. I could say plenty of it, but now we will switch to Thierry. The idea is to give you more from an industry point of view.
So good afternoon. Okay. So good afternoon, everyone. I'm Thierry Debucher from Thales, and I'm working in the corporate laboratory, research laboratory of Thales in Palaiseau near Paris. I'm not a software guy, I'm a hardware guy, so I will give you a little flavor of what physicists are doing to build a quantum computer. You can see in this slide that there is a lot of actors in the field of quantum computing. Comment on revient en arrière? Okay. So you have users, which will define the use cases that have to be addressed with the quantum computer. There are a lot of companies also developing software and investigating applications for these quantum computers. And then as you need a quantum computer, there are several companies that are developing quantum computers, the physical support, the physical platforms. Which will address, there are a variety of techniques for that. And well, since I'm not a software guy, I will focus on these physical platforms. Okay, so I skip this. Well, you have my address if you're interested. Just a very quick word on the landscape of quantum research that is supported by the European Commission. There is a quantum flagship in the center, which addresses the 4 pillars: computing, simulation, communication and sensing, and basic science. And so these are projects funded by the European Commission. And around this, there are other initiatives, and in particular, there is one which is EuroHPC that Laura has just mentioned, which will, the target is to combine quantum computer with supercalculators in order to increase the power of supercalculators. So I will not describe all these other actions. But here, if we focus on quantum computing, you have here a list of the main platforms that are used. That are developed by physicists to be able to build in a time the quantum computer. So it goes from superconducting circuits with startups which are active in the field which are here, many of them, and the corresponding European project that supports this research. And then you have neutral atoms with other startups, trapped ions, photonics, and there is here in the exhibition there is QUIX, which is developing photonic circuits for these photonic platforms. You have also quantum dot spins. This is based on electronic circuits developed with these startups here, and NV centers in diamond, which are defect color center in the diamond, developed by those companies. So I will not detail all of these platforms, but briefly I will go to 2 of them, which are the main ones, the most advanced ones. The first one uses trapped ions, and you have here a scheme of the system. So you have single ions, which are here trapped in an electromagnetic trap. All the ions are distant in a controlled way, and they can be controlled with a laser beam, and then we can modify the state of this ion depending on the laser beam. And all those ions interact, and this is here a picture of this ion. So each spot here is a single ion, and all of these interact and then produce quantum states such as superposition or entangled states, which were described previously. And there is a company which is Alpine Quantum Technology, which is in Innsbruck, and which is developing a machine based on this technique. And you can see here that this is a real machine that you can implant into your laboratory. And at the moment, they are able to address 20 to 30 ions with this machine, and they plan to develop this, of course, to address larger size of calculations. And there is also a cloud access possible with this machine, so that you can put your software and try it on this machine. So this was for the first example. Second example, neutral atoms. This is the idea here is to have single atoms that are located in a network, in a grid which is produced by lights. So you have laser beams which interact that produce some wells here, and in each well there is a single atom. All of these atoms are coupled so that they can interact, and this way, by interacting, they can they can simulate a quantum algorithm. You have here a picture of all these neutral atoms that are trapped in the light trap. There are around 300 atoms here. So this is a research effort, and the target is to address chemical processes in molecules or new pharmaceutical developments. And there is a company that has been launched a few years ago, which is developing a complete system, a full stack system. You can see here the machine which is implanted, and they are able now to address 100 qubits, and they of course intend to go higher with the more qubits. And interestingly, they have a lot of interactions with big companies, EDF, Thales, WAICF, Siemens, and so on, to address various use cases in a large variety of fields of applications, in order to see how these simulators can improve the simulation and the calculation which these companies are needing. Last example is superconducting qubits. So here, this is an electronic circuit with wires, and there are here, what are the qubits? These are what they call Josephson junctions. So this is made of niobium circuits, which are cooled down at very low temperature, close to the absolute zero, few tens of millikelvin. And when you cool down an electronic circuit in this range, it behaves like a quantum object. And you can play with the qubits and do some calculation. And you need some cryostat, which is represented here. And when you develop this, you can build industrial machine, which is represented here, and which is developed by the company IQM in Finland. And now they are able to manipulate in the order of 150 qubits in their computer. So this shows that there is a lot of developments with these platforms, and the progress is very impressive. And now they are starting to combine these calculators with supercalculators. And this is a slide giving some details of what Laure mentioned previously. So this is the HPCQS project developed in the framework of the Euro-HPC joint undertaking. And there is 2 machines from Pascal that will be combined with a supercalculator, one in Jülich, close to Cologne, and one in Paris. And they are starting to operate them, to combine them in order to increase the efficiency and the power of supercalculators. Then the quantum computer is used as a coprocessor. It will accelerate some tasks for this computer. So this is under development, and there is a last development which is also supported by the Commission, which is to develop a network of quantum computers all over Europe. So you can see here there are 6 of them that are planned and that are being developed at the moment in various countries. And just to finish. No, there is no. Okay, so I had a slide with the sensing. It's not here. Well, anyway, you can also use another point is how to use artificial intelligence for other aspects such as sensing or communication. And then, for example, we've seen that it's very useful to analyze images or to improve images. And in sensing, we have a lot of applications where sensing is where you have to manipulate images, and it's a way to improve this. But well, okay, I will stop here, and okay, I think this is the last slide of the presentation. Okay, so now maybe there is some time for questions.
So we are just in time, but we started 10 minutes later. Thank you. So I think, again, as a conclusion, this was really a broad overview. I don't know if you catch it, but you can have a specific look in all those details. The idea was really to give you a sense of, okay, it doesn't come out of the blue. It will not replace everything. And there is a link with AI, and so there is probably a future for some of you, and it's typically an area where we have to be creative as well. We have to think out of the box. So I think we can take questions. Sorry.
Thank you. For machine learning, I want to ask if it's not, I mean, from the normal, we know you give an input, we know the output, but machine learning, you don't know the output. And for finance, we see now in China, crypto yuan, and Elon Musk want to build everything up. So they make payments, like in WeChat. So how do you see you in 5 years when money is just a story now? Thank you.
Well, okay. Now it works. Sorry. I think that this question is not totally related just with quantum computing, but let me say with digitalization process that financial institutions are facing and sometimes have, let me say, have already started. So of course, I can speak in behalf of Intesa Sanpaolo. So it's not a general, of course. Of course, there are other financial institutions that are doing something similar to what we are doing, but I want to speak just for the company I represent. With this industrial plan, current industrial plan, let me say we started a new phase. So we complete the transition from a standard bank with branches and so on to a completely digital bank in the previous industrial plan. And that's why, for example, the mobile app of Intesa Sanpaolo is the first mobile app in the world for foresters. So we've done a lot on this. And during this let me say, this current industrial plan, we are pursuing the second step, that is, of course, to, let me say, as our chief data artificial intelligence and technology officer says, we need to transition from a digital company to a tech machine. So basically, and this is related to, let me say, a vision in which banking is going to change from, let me say, traditional economy to platform economy. And that's why you need to integrate financial services, for example, in platform. So you need to contextualize financial service in digital platform, like, for example, WeChat in China. And so you can basically enable digital payments through a chat system.
Free digital payment, which you cannot allow.
Yes, the point is that. No, the point is that this is, of course, a matter of regulation. So it's not a call of a financial institution. What a financial institution can do in order to be prepared, in order, let me say, to have business tomorrow, is the fact that you can be the provider of this kind of technology. So even if let me say, the payment is going to be free. I'm not sure of that, of course, because it depends on the regulation, no?
If I buy from China now, I pay with WeChat for free.
No, okay. But this is just in China. So it's not something that is necessarily allowed everywhere. Okay, this is a call of the regulator. But the point is that even in this scenario, imagine that let me say, the bank is going not to have the revenue from the transaction. You could still have a revenue if you are, let me say, the provider of the services that is integrated. And that's why you need to, let me say, you need to pursue this transition from a digital company, classical digital company, to a tech machine. So you need also to provide the service.
So long
Well, I disagree with you because Intesa Sanpaolo launched the first.
We have to leave.
We can continue, but I disagree with you because we launched.
Is there any other question before we leave the stage for the next one? Okay, thank you. So I left here for the quick, if you are interested and want info, and of course you can ask us individually. Thank you all, and have a nice weekend.